Hi friends, in this video we are going to discuss about the concept of torque equation. Okay, so how we are going to get the torque equation of a three-phase induction motor. Okay, so in this video we are going to solve, or we are going to derive the derivation of torque equation of a three-phase induction motor. Okay, so actually this torque equation is we will get this torque equation in two conditions. Okay, one is what? One is standstill condition of a rotor, and the second one is running condition of a rotor. Okay, so standstill condition of a rotor, it means that the rotor is at standstill. It means that what? Rotor is not rotating. Clear? And running condition of a three-phase induction motor means definitely the rotor will rotate. Okay, so we are going to get the torque equation for both the condition. Okay, one is for standstill condition and another is for running condition. Clear? So if you want to get the torque equation under standstill condition, you no need to go for the concept of rotor frequency. Okay, but if you want to get the torque equation under running condition, then you must to go for the concept of rotor frequency or rotor current frequency. Okay, so without knowing the rotor current frequency, you cannot get the torque equation under the running condition. Okay, so that is the reason why first I will start with the synchronous speed of a induction motor, and after completion of synchronous speed, I am going to discuss about the slip, what is slip and what is a percentage slip formula. And after completion of this slip, I am going to discuss about the rotor frequency, and after that I am going to discuss about the torque equation under standstill condition as well as running condition. Okay, so here first thing is standstill condition. Okay, so standstill condition, very important topic, torque expression or torque equation. Okay, standstill condition of a rotor. Okay, here the meaning of standstill means constant means the rotor is not rotating. Okay, so you know that. So just see here, just I am explaining about the stator and rotor with the help of this diagram. Okay, for example, this is the rotor, for example, just assume, and this one is the stator. Okay, so this is a stator, and this inside of the circle represents the rotor, and between this stator and rotor you have some air gap. Okay, you have some air gap. So whenever we are going to apply three-phase supply to the stator of a three-phase induction motor, so there is a production of rotating magnetic field. Okay, RMF means rotating magnetic field. So this rotating magnetic field is always rotates at a synchronous speed. Okay, so that is the reason why first we are going to start with the concept of synchronous speed. Okay, so the speed of the rotating magnetic field is always rotates at a synchronous speed. So here n suffix s represents the synchronous speed of a rotating magnetic field, and the expression of this synchronous speed is given by ns is equal to 120f divided by p, and here revolution per minute. Okay, so this ns is equal to 120f divided by p in rpm. So this is the speed of the rotating magnetic field on what? Stator of a three-phase induction motor. Okay, now assume this is equation number 1. Clear? Now this is clear. It means that just we are discussing about the rotating magnetic field on what? Stator only. Okay, till now I didn't speak about the rotor. Now coming to the rotor. So as per the concept of working principle of a three-phase induction motor, definitely we need to rotate the rotor with the help of the working principle. Okay, so that is the reason why our target is to rotate the rotor. Okay, our target is to rotate the rotor. So I am talking about standstill condition. Standstill condition means the speed of the rotor is 0. Okay, so that, for example, I am here considering as, for example, n represents the speed of a rotor, and under standstill condition, okay, under standstill condition, the speed of this rotor is 0. Okay, so that, so the speed of the rotor is 0 under standstill condition. Okay, I assume this is equation number 2. Now if you know the value of synchronous speed of a rotating magnetic field, and if you know the speed of the rotor, that is under standstill condition, the value of speed of the rotor is 0. Okay, if you know these two, now we can go for the concept of slip. Okay, so what is slip, and how we can define the slip? Okay, so here slip is the most important concept, and without the concept of slip we cannot get the torque equation under running condition. Okay, so that is the reason why slip is always represented with S. Clear? Now slip is defined as the difference of synchronous speed of a rotating magnetic field and the speed of a rotor. Okay, just see here, n suffix s, it means synchronous speed. Synchronous speed is the speed of the rotating magnetic field, and here n represents the speed of the rotor. Okay, the difference between the speeds of rotating magnetic field and the rotor is called as slip. Clear? So you can directly say that S is equal to ns minus n. Clear? So S is equal to ns minus n is the difference between what? Difference between the rotating magnetic field speed and the rotor speed. But whenever we are going for the analysis, we always define the slip in the percentage. Okay, so that is the reason why if you want to represent, or if you want to define the slip in percentage, so you can directly define, or we can directly give the expression of this percentage slip with respect to what? Synchronous speed. Okay, so that is the reason why, so percentage S is equal to ns minus n divided by ns into 100. Okay, so this is the expression of percentage slip, and I assume equation number 3. Okay, now we have equation number 1 is the expression of synchronous speed. Equation number 2 is what? Under standstill condition, the speed of the rotor is 0 rpm, and here the point number, equation number 3 is what? Percentage slip. Clear? Now we are going to get the percentage slip under standstill condition. Okay, so now you can observe here, so percentage slip S is equal to ns minus n divided by ns into 100. Now you know that under standstill condition, we know that n is equal to 0, because the rotor is not rotating, so that n is equal to 0. So with the help of this, so percentage slip is equal to ns minus 0 divided by ns into 100, so that ns divided by ns into 100, so ns gets cancelled, then you will get 1 into 100. Okay, so here percentage slip is equal to 100%. For example, if you want to represent the value of slip without percentage, so we can directly say that S is equal to 1. It means under standstill condition of a rotor, the value of slip is always 1. Clear? So I assume this is equation number 4. Clear? Now coming to the another point, for example, I am writing here in the new page. Now I think you are clear. Under standstill condition, the speed of the rotor is 0, so that slip is equal to 1 under standstill condition. Clear? Now condition number 2, that is what? That is running condition. Running condition. So running condition of rotor. So running condition of rotor. Running condition of rotor means rotor is rotating. So rotor is rotating means the speed of the rotor is definitely not equal to 0 rpm. Okay, so under running condition of a rotor means rotor is rotating. Rotor is rotating means definitely n is not equal to 0. Okay, under this case n is not equal to 0, and here ns is equal to, for example, some value of the rotating magnetic field, for example 1000 rpm. Okay, for example I am considering just 1000 rpm, and for example under running condition of the rotor, for example the speed of the rotor is, for example, at 900 rpm. So that what, now there is a presence of n and there is a presence of s in what, slip. So here ns is equal to ns minus n divided by ns, that is equal to 1000 minus 900 divided by 1000. Okay, so here you are getting 100 divided by 1000, so that 2. Okay, so you will get what, 1 divided by 10. So we can directly say that 0.1. so s is equal to 0.1 slip. Okay, the value of slip is 0.1 when the rotor is under rotating condition, and when we are considering, just when we are assuming the value of n is equal to 900 and synchronous speed is equal to 1000 rpm. It means that what, s is not equal to 0, s is not equal to 0 and s is not equal to 1. You are getting some value of slip. Okay, and please remember the value of s, or the range of s is always from 0 to 1 only. Okay, this is most important point. Okay, slip in induction motor is always from 0 to 1 only. Okay, under standstill condition of the rotor, the value of s is equal to 1, but under the running condition of the rotor, you are getting the value of s is not equal to 0 and s is not equal to 1, so that you are getting the value of slip s is equal to 0.1. Okay, so this is about the concept of slip under standstill condition and running condition of a rotor. Clear? Now coming to the third concept, that is rotor frequency. This is most important concept. Okay, rotor frequency. Okay, for example, I am considering rotor frequency. Here fr represents rotor frequency. Just consider for up to this topic only. Okay, and don't consider as fr represents the resonance frequency. Okay, so just we are talking about rotor frequency. So to understand, just I am giving the name for the rotor frequency as f suffix r. Clear? So here f suffix r, that is rotor frequency. Now rotor frequency is always same in case of standstill condition of a rotor. Okay, it means what, when the rotor speed is 0, rotor frequency is always follows the supplied frequency. Okay, so where f is represent the supply frequency, then under standstill condition of a rotor frequency is always is equal to supplied frequency. But under running condition of a rotor, so this rotor frequency is not equal to supplied frequency. Okay, so but how we are getting this fr is equal to f and fr is not equal to f under standstill condition and under running condition? Now we will discuss, and I will give you the proof for these two conditions now. Clear? Now here the most important point is, under running condition of a rotor, we can directly say that rotor frequency is not equal to supplied frequency. But under standstill condition of a rotor, the rotor frequency is equal to supplied frequency. Okay, so that is the reason why what we are doing, so we are talking about rotor frequency. Okay, so we are talking about rotor frequency, so f suffix r. Clear? So you know that you have the standard expression of synchronous speed, and synchronous speed, that expression consisting of frequency. Okay, so you can directly consider ns is equal to 120 f divided by p. Okay, so this is the synchronous speed of a rotating magnetic field RMF. Okay, so from this I can directly write, so F is equal to Ns into P divided by 120. Okay, so this is the expression of frequency. Okay, now we are talking about rotor frequency. Okay, rotor frequency is always depending upon the standstill condition. Okay, you can observe here we are talking about what? Rotor frequency is follows the supplied frequency under standstill condition, but rotor frequency is not going to following the supplied frequency under running condition. Okay, it means that what we need to consider the speed of the rotor under standstill and speed of the rotor under running. Okay, so for this purpose what I am doing, just I am modifying this expression. Okay, just for understanding purpose. Okay, so what I am doing, FR, it means rotor frequency is equal to N. Okay, this here I am writing N into P divided by 120. Okay, so P represents the number of poles. P represents the number of poles, where N represents the not rotor. Okay, this is the relative. Okay, relative speed between Ns and the rotor speed N. Okay, so here what I am doing, instead of Ns, just I am placing N, where N represents the relative speed between the Ns and N. Okay, so that is the reason why you can observe here. So relative speed means how we can write this expression, we can directly write Ns minus N into P divided by 120. Okay, so the unit of frequency is always hertz. Okay, just to be modified, we modified this expression into this expression. Okay, don't confuse, just I am modifying to prove the rotor frequency under standstill condition as well as running condition. Okay, now here N represents the relative speed between the synchronous speed of a rotating magnetic field and the rotor speed. Okay, now you can remember this expression to prove that condition. Clear? Now you can observe here. Now you can observe. So now what we are doing, first we are going to consider the standstill condition of a rotor. Okay, so what is the expression we got now? Fr is equal to Ns minus N into P divided by 120. Okay, so first we need to consider, we need to write that expression here. Okay, so Ns minus N into P divided by 120. Okay, clear? Now first we will discuss about the standstill. First we need to discuss about the standstill condition. Okay, now see, standstill condition means rotor is at rest. It means what? Rotor is not rotating. So that standstill means N is equal to 0 RPM. Okay, N is equal to 0 RPM. Now what we need to do? We need to substitute the value of this in this expression. Okay, now it will becomes what? Fr is equal to Ns minus 0 into P divided by 120. Then it will gives N into N suffix S into P divided by 120. You already know that previously we have written Ns is equal to 120F divided by P, where F is equal to Ns into P divided by 120. It means that this term is repeating here, so that instead of Ns into P divided by 120 we can directly write F. So that what? Under standstill condition of a rotor, rotor frequency is following the supplied frequency. Okay, this condition is proved. Now condition number 2, that is what? Running condition. So here the running condition of rotor. Running condition means what? Rotor is rotating. It means N is not equal to 0. Okay, sorry. Yes, N is not equal to 0. n is not equal to 0 means definitely some value of speed is there because rotor is rotating. So in that condition, we cannot substitute the value of n is equal to 0 in this expression, rotor frequency expression. So f suffix r is equal to ns minus n. So we are writing as it is. So into p divided by 120. Okay. So we are not substituting the value of 0 instead of this because rotor is rotating means the value of n is not 0. So that I am writing ns minus n into p divided by 120. But what is ns minus n? What is ns minus n? So for this term you have the concept of slip. Slip is equal to ns minus n divided by ns. So that we can directly write ns minus n is equal to s into ns. It means instead of ns minus n, I can directly write s into ns. So that I can directly place s into ns into p divided by 120. Okay. Now just what I am doing, just I am separating these two terms. Okay. So here s into ns into p divided by 120. You can observe here again this ns into p divided by 120 represents the frequency only. It means that what you are getting s into, instead of this term I can directly place f. So that is the reason why under running condition of a rotor frequency is not equal to f. Rotor frequency is equal to slip times of the f, slip times of the f. So that is the reason why rotor frequency is not equal to supplied frequency under running condition of a rotor. Clear? So if you are clear with these topics, then only you can easily understand the concept of torque expressions. Clear? So I think you are clear with this topic. So I am going to upload the another video of the torque equation of a three-phase induction motor under standstill condition and also the running condition of a three-phase induction motor with the help of whatever the topics we discussed here. So all these topics we are going to use to get the torque equations under standstill condition as well as running condition of a three-phase induction motor. Okay. So thank you so much for watching and please do subscribe my channel for more updates. Thank you.